Hello. This video is going to be about doing a system identification on a second order plus dead time temperature system and computing the controller gains. And the end result that we want is going to look like this. Okay, so what I got was a file in 2005 where there's a control output and there was the process value or the temperature, which is the cyan line. And the goal is to compute the parameters that will give a differential equation that will uh, simulate the actual response. And what I was provided with is a comma separated or space separated variable file where there was a time in seconds, the control output in percent, and the process value in degrees. And I think this is Fahrenheit. And this data came from a training class where the instructor was teaching people how to do temperature control using wood burner kits. So they had a little wood burning iron with a temperature sensor on the end, and they were pulse width modulating the AC to control the temperature. So this was gathered by a trend, and then it got imported to Excel and exported as a comma separated variable file. So this is the file that's being read by this program. It's a second order plus dead time, and it says LSQ for least squares. So to get started, these are my imports, and normally I use the uh, optimize minimize function, but in this case I'm using the least squares. It's actually the best of the bunch when it comes to doing system identification. And I need to have ODE in to simulate the differential equation or the system. The cubic spline is necessary because if I'm simulating a dead time or trying to determine a dead time, I might have a dead time of a half second. I need to interpolate in between. This file reads the comma separated variable file, and this file makes the plot. I have a print the parameters routine, print the results, and then I have a calc PID routine. And in another video, I will show how I come up with these formulas. This is the formula for the controller gain, where you have a time constant, the open loop time constant, 0 and 1. There's two time constants. Uh, this is the open loop gain. This is the controller gain. And then this is the closed loop time constant and a dead time. So this is the integrator time constant and the derivative time constant. I have initializing the parameters, and this is somewhat close, but actually the dead time is off by quite a bit, and that does cause some problems for the auto tuner. Then I have the differential equation, and I have a parameters. Y is the process value and the process value rate, and T is an array of times or times. So the parameters are the open loop gain, the two time constants, an offset, which happens to be the same as an ambient temperature, because when you turn the power off, the output will not go to zero. It'll go down to whatever the ambient temperature happens to be. And then I have a dead time parameter. So this does the interpolation in between the time readings so that I can handle the different dead times. And then this is the differential equation for the, simulating the temperature system. And then I return an array of, this is the processor temperature rate and the second derivative of the rate. And this gets integrated by the ODE int to generate an array of temperatures and temperature rates. So this is the ODE int, and it's making the array of estimated values, which I'm going to compare with the actual process values or temperatures. And I'm computing the mean square error here, and I can print the mean squared error plus how the parameters are changing here. And I'll get back to this in a moment. But this way you can actually see what is happening when the algorithm is working. This is my second order plus dead time routine, and I'm planning to have a first order plus dead time, but usually a system only has a second order plus dead time unless you want to ignore one of the time constants, which I don't want to do. So this is the main routine, and basically this reads the data, and then it calls the second order plus dead time routine, prints the results, calculates out the PID, plots the array, and that's it. So if you want to go over or see what I'm doing here in a little bit more detail, freeze the video. Now let's talk about the results over here. What's nice about the least squares routine, and I think it's actually the Levenberg-Marquardt routine, is it not only calculates out a gradient, but it calculates out a Hessian or a second derivative gain. I know I've seen the code in C, and I know that it generates a Jacobian anyway. So these are the first 5 guesses, and it has to figure out the slope and Jacobian from that. And you can see that it makes a very good guess for the parameters on its first iteration. So then you get 5 more, and then it does another 5. And then you can see as it gets closer to the real solution that the changes are slower, lower and lower and lower. In other words, the gradient is less and less. And then it prints out uh, the time, this is very fast. And then I can change this xtoll to make it so that it goes a little bit longer, maybe get a little bit better result. In other words, reduce this mean squared error. Oh, and I'm using the mean squared error for a reason. The reason why is that the system happens to have some very sharp values or valleys. And by dividing by the number of readings, in other words, I'm dividing the sum of squared errors or the dot product by the number of values, I make it so that the terrain isn't quite as rough. And I will get to that later, probably in another video. It prints out the root mean square, the open loop gain of the system, the time constants, the ambient temperature, and the dead time in minutes. And that's basically what you're seeing here. So just looking at the data, oops, that was the previous one. You can see what is changing. These are my initial guesses, and then you can see how the gains are changing as it goes through all the iterations. And there aren't that many iterations. There's uh, 8 Jacobian evaluations and only 17 iterations. So you can see that the least squares algorithm is very, very efficient. And then finally, I'm printing out the closed loop time constant, which is um, the shorter I make this, the faster the response is going to be. The controller gain is that's the number of degrees per unit of error, and the unit of error is degrees right now, or this amount of control output per unit of error. So if I wanted to have to increase the temperature by 145 degrees over ambient, I'd have to put out 100%. This is the integrator time constant. This is for an ISA version of the PID where you have the controller gain, and that's multiplied by 1 times the integrator time constant um, divided by S, and then you got the derivative time constant. And these are all in minutes, and that's multiplied by S. So this is the derivative time constant. So you can see that there isn't that much to writing uh, the program to do the auto tuning. And people have actually used this, or they've used a previous one I had written in Scilab to actually tune a system. And the person who did it used my Scilab program actually wrote a TK interface for it, which was kind of nice. And he posted that on the forum. But anyway, I want to now go over to the optimize minimize routine, and that is here. Let's see, that's here. Okay, now this one it's basically the same thing, except for I'm using come down here. I'm using Nelder-Mead, Powell, congruent gradient, BFGS. This is Broyden, Goldfarb, or no, um, guess I forget, Goldfarb and Shannon. Forget what F is for. But anyway, this is basically the same routine after you get past this point. So I'm going to run this using the Nelder-Mead. So I'm just going to run it. And you can see the Nelder-Mead takes a little bit longer, does a few more iterations. It actually gets a little bit better answer. This mean squared error is a little bit less, but it takes a little bit longer. But you can see that it still gets a very good result. And the advantage that the Nelder-Mead has is it doesn't require derivatives or Jacobians. And that's really nice whenever you have noisy data. And from what I've seen, the Nelder-Mead always seems to work. It could fall into a local minimum, but I have never had that problem on a auto-tuning system. And I'll get more into that when I talk about gradient descent. Another system that works is the Powell's method. And I'm going to comment out the Nelder-Mead and use the Powell. And Powell is a lot more complicated than Nelder-Mead. Um, Powell actually starts out with 5 different vectors for the 5 different parameters, and it does a line search in each of the directions. Then it uses the minimums that it finds to construct new lines. And I have an example with the valve ID. There's another video, and there's 15 parameters, and I don't see how it ever finds a minimum there with the 15 different lines. But anyway, let's just run this so you can see how long it takes. And this won't take too much longer. You can see that the mean squared error is getting down there, and it gets the same thing as the Nelder-Mead for the mean squared error, but it takes a little bit longer. And for the amount of effort that this takes, I would rather use the Nelder-Mead. But the Powell's method works well because and systems that are noisy because it doesn't use the derivative gain again. Um, I'm not going to go into the congruent gradient or this BFGS or the limited memory BFGS um, method because they use the gradients and they take a lot longer to solve in this case. I know that the BFGS uses a Hessian, and it actually gets an error saying that it runs out of precision because when the gradient gets to be small, it gets kind of lost in the noise. So for doing auto tuning, I like the least squares, I like the Nelder-Mead, and the Powell's method because they don't require derivatives. So hopefully you can see how these parameters are getting smaller and smaller. Oh, then to explain this part, well, I told you that the Powell's method starts out with 5 different line vectors, and they go in arbitrary directions, and sometimes they're not the right direction, so you get these very large uh, mean squared errors, and so then it has to backtrack and go the other way. But eventually it does find the right answer. But um, I have had problems with the Powell's method blowing up and getting some of the squared errors or mean squared errors that are so big that they crash. And that's because I have, in this case, I got 1,200 samples. And the more samples, the larger the mean squared error can be. So if you make bad guesses or you go in the wrong direction, it's possible that you get an overflow error and the system just stops or crashes. So that concludes my video on doing second order plus dead time uh, system identification and calculating the gains. Hope you enjoyed it. Bye.